thank you organizers for inviting me to this great workshop. So Belen talked about contextuality yesterday in a graph theoretic approach. Today I'm going to talk about a closely related approach called sheaf theoretic or topological approach by Samson and Adam Brandenberger. And I'm going to I guess Samson has been lecturing about this approach a lot, I guess.
Very, very long time.
Oh, okay. Then I'm going to remind you what this approach looks like. And then I will give you a bit of a logical reflection on this, and then I will give you a bit of new results. But anyways, I will go to the, let's cut to the chase. So in this topological approach, we are going to deal with contextuality as a sort of a matter of the topology of data in a very general setting or general formalism. So it can be about, the formalism can be about variables and values of those variables in general. For instance, you can talk about measurements and their outcomes, or in relational databases, you can talk about attributes and data values, or if you apply this to logic, you can talk about sentences and their truth values. So the basic common structure, formal structure, is just the following. So we have a set of variables, and then I'm going to add for each variable, I'm going to take a set of values. They may intersect with each other, but I'm going to take a disjoint union of them in this way. Or say, you can say this is a dependent type, so you're going to take a dependent sum. Anyways, the point is that you have two sets, set of variables and set of say question answer or variable value pairs or something like that. So you have two sets. Now I'm going to add a topological structure on top of this. And then I'm going to, topology can be about many things, but there are two aspects I'm going to use a lot. So first aspect is that topology distinguishes what is a good, continuous section, what is continuous and what is not continuous. Yeah, like this. This is a continuous section that is not. The continuity breaks down there, and so on. The other aspect is that topology tells you, given a sort of a set or space of points, it tells you how you can move around in that space. So in this case, from blue to green, you have to pass a red point, or in here too. If you start from here to go there, you have to cross a red line, and so on. So the topology is about how you can move around too. So there are two aspects I'm going to use in this formalism. So the first comes in when you observe that, sometimes you can ask several questions at once, but answers you get from, say, physical systems or relational databases or the model of logic in front of you may obey certain constraints. For instance, if you are sort of measuring temperature and volume of a gas in front of you, then they are in proportion to each other. So the values must be correlated with each other. Or in logic, if you say take those sentences, phi, not phi, then their truth values may be anti-correlated. Must be anti-correlated, right? So the point, you can also talk about relational databases, and you can talk about, say, Samson Abramsky, University of Oxford, and so on in a relational database. So the point is that models in front of you are going to distinguish good and bad ways of connecting dots. So in the first slide, I used introduce dots. Now you are going to, now the topology is going to tell you what is, or the model, the constraint of the model is going to tell you what is a good way of connecting dots, what is a bad way of connecting dots. That's as in this. So it's how the topology comes in, because topology is about distinguish good and bad ways of connecting sections. Is that all right? Okay. The second aspect of topology comes in when you observe the following. So when you make a query, or when you make a measurement, those are several values, or variables, or several measurements at the same time, then they are going to form a measurement context. But, so those are the examples we saw, but we may not be able to get to, say, measure or ask or those queries concerning other set of variables. For instance, the variable set V may be too big to, query or deal with feasibly, or database schema may not have a table encompassing all those attributes in V, or in quantum mechanics. This is what Belen was talking about yesterday. So Alice has to choose one measurement from two measurements, and then Bob has to choose one from two measurements he can make. And then those cannot be made at once, those cannot be made at once, those can be, and so on. So in the end, you're going to get those combinations of sets of measurements that can be made at once at the same time. Now, so the point is that the family of contexts of measurements that can be made at once is going to form a simplicial complex that is a downward closed family of finite subsets of all the measurements. So it looks like this way, or if you look at this way, this is a simplicial approximation to a circle of the kind that we saw in the previous slides. Okay, so these are two topological aspects in the model. Now, I'm going to define a topological model as just those two sets with topologies on top of each other. So formally speaking, a topological model can be defined in two ways. First, you can consider that as a presheaf, assigning to each measurement or to each variable, you're going to assign the set of possible values of that variable. And for each combination of variables that can be measured together, you are going to assign the set of good combinations, good ways of connecting dots. So in this model, in this particular example, I'm going to throw in all the 4 possible combinations, meaning that this model doesn't have any constraint about the possible values of those variables. But on the other hand, I'm going to omit above this context, I'm going to delete this edge, meaning that this model expresses a constraint that 0, 0 cannot be measured at once. So if Alice chooses this measurement and Bob chooses this measurement, then the outcomes, the possible combinations of outcomes they can observe is 0, 1, 1, 0, 1, 1, but not 0, 0. Is that all right? Okay, so the same thing happens here, and a similar thing happens here too. So if Alice chooses this, Alice measures this, Bob measures this, then 1, 1 is ruled out. That's how the model expresses the constraints. So you can say this is a presheaf assigning all the possible combinations of values, and then you're going to say it assigns relations, blah, blah, blah. So technically speaking, it is a separated presheaf, but anyway, that's not so important right now. Or another way of looking at it is that this forms another simplicial complex. So this is a simplicial complex over simplicial complex in a certain way. But this is not, this is just a formalism. So far, the idea must be in this picture. All right, so yeah, okay, this is assigning. But now, more important thing is that if you look at this topological sort of a bundle, this guy sitting on top of this guy, you can find what is called a global section in this space. This is a sort of a copy of downstairs in such a way that everywhere this red circle obeys the constraint above every context. So, definition, formally, a global section is a function from here to here so that you can go back to the original in the way everywhere the constraint is satisfied by that function. Yeah, okay, so this is a easy idea, but the point is that this global section amounts to assignment of values to all the variables. This is a global section, not just local section. So this is going to assign all the values to all the variables in a way consistent with every constraint in the model. Yeah? So for instance, if you look at this as expressing something about logic, models of logic, then global sections are exactly the models of a propositional logic, classical propositional logic, because those global sections are exactly the assignment of truth values to all the sentences in a way consistent to the laws of logic. Right? So you can say this consistency of the sentence X is equivalent to send it to, hey, X is true, and you're going to see whether that can extend to some global section or not. That's what the consistency of that sentence is about. Okay, but so yeah, okay. Think of it this way. You may think that so in the physical context, you may think of this as a state of a physical system. For instance, in the case of a gas in front of you, you may be able to. Maybe you are only going to measure temperature and pressure of that gas, but all the other physical magnitudes are already assigned in the physical, already there in the gas. So, well, it may seem natural for you to think that, okay, so those global sections are the state of physical systems. Well, okay, that assumption is good in classical mechanics, classical physics, but not in quantum mechanics. This is exactly what the contextuality is about. So let's take an example from quantum mechanics that violates this assumption. That is actually the example I took 2 or 3 slides ago. This is a model found by Lucien Hardy, and the point, well, one point is that sometimes you can see a global section like that. So the idea is that if Alice chooses this, Bob chooses this, and if they observe, say, this combination of outcomes, then they can, or we can, explain the situation by saying that maybe there was a global assignment of physical magnitudes to all the physical, values to all the physical magnitudes, and Alice and Bob just, observed that. But on the other hand, if Alice chooses this, Bob chooses this, and observe this combination of values or outcomes, then the point is you cannot extend this to a global section in a way consistent to all the constraints in this physics. So the point is that as soon as well, okay, that's too quick. As soon as they observe this combination of outcomes, that kind of global explanation is all the bets are off. You cannot say there was say Alice and Bob chose this measurement context, and you may want to say that, well, the measurement is context independent. Independently of that choice of context, there was a physical magnitude already in the system. You may want to say that, but no. Because there's no global assignment of values to those physical magnitudes that are consistent with all the constraints. You have to accept that, okay, this joint outcomes was essentially dependent on the choice of measurement context, hence contextuality. So Samson's idea of characterizing contextuality is to use the topology of data alone and to say that contextuality lies in obstruction to the extension of this section to a global section. Yes?
When you say context, what are you referring to? The object in the base there?
Oh, yeah. Yes. So when I mean context by a set of measurements that can be made at once in the physical context.
Okay, so A0, B0, A1, that would not be a context because...
Right.
So it's just a simple Caesar.
Yeah, that's right, yes. Of course, you can talk about some section on top of this, illegal
I'm just
context.
And the word context.
Yeah. I mean, yes, I'm going to use context as valid or no, a legal set of variables. I mean, legal in the sense that they are in the physical context or in quantum context, that those are the sets of measurements that can be made at once.
Objects of C.
Yeah. That's right. All right, so far so good. Oh, okay. I'm a bit spending too much time on this. So, moreover, if you sort of start thinking of contextuality this way, then you can think of a even stronger kind of contextuality like this, because this is the model Tobias discussed in your talk now. Anyway, this is a correlation, and anti-correlation. So hence, this is going to sort of there's no global section for this model. So this is even stronger than this case, and it's called a strong contextuality. So the point is, the slogan is that the contextuality consists in a local consistency but global inconsistency. So within those measurement contexts, they obey constraints in a way consistent to given physical constraints, or even this context and this context sort of interact with each other, which I'm going to talk about later. But so this local consistency doesn't entail global inconsistency, because sometimes the section cannot extend to a global. That is contextuality. Anyways, this is a little small remark. So non-locality in this picture, non-locality amounts to just a special case of contextuality implemented by using spatially separated systems and composing them together. Hence, contextuality in that context would amount to non-locality, but also there's a probabilistic version of this as well, which Kohei is going to talk about that, so I'm going to sort of be quick about that. So look at this model. This is not logically contextual because every section extends to global. But if that happens, you can see that then this is just a disjunction or possibility mixture of the global sections, right? Can you see that that's the case, if and only if? Okay. So if you're going to replace that possibility mixture with probability mixture, then you get a probabilistic contextuality, as in Bell non-locality theorems. But I'm going to skip over. So this is a probability 1/2 of this global section. This is 1/2 of this section, and then this model is not contextual. But Bell's theorem states that this cannot be realized that way. But anyway, that's a probabilistic part. Okay, there's one more thing. Okay, so the point is that quantum mechanics behaves weirdly sometimes. Now, but even those weird paradoxical systems must satisfy the following condition called no signaling principle in the following, which amounts to the following condition in our setting in this possibilistic case, meaning that this model is no signaling if and only if every restriction of those combinations to smaller combinations is a surjection or an onto map. Why does it mean no signaling? So let's talk about the failure of no signaling. Yeah. So here I'm going to delete this section so that this is a violation of this formal condition of no signaling. Why does it kind of signals? Well, because in this case, if Alice pushes this button, Alice can push this button or this button. Alice chooses this button, and suppose Bob observes this. Then if this constraint is really the case, then Bob can infer that, well, because this is, possible with this one, but not with this one, so Alice must have pushed this one, even if Alice and Bob are separated, far, far away. So this is no signaling. And then so it's a kind of a relativity-ish principle, but also in a relational database, it's about consistency among tables. So we usually take this as part of the, yes?
How is it about consistency among tables?
So suppose this is a one table in the relational database and one relational database. Then this table is going to say that, hey, this guy is in. And this table is going to say this guy is not. Restriction? I'm sorry. Sorry.
Projections onto the attributes.
Yeah. So whether this is in the database or not depends on this table and this table. So those tables are not going to agree with each other with respect to whether this value is in the.
Okay.
Yeah. I mean, in a consistency or coherence, maybe. Of course. I mean, the tables.
I mean, if the bundle over B0 is all strings or something, it would be that every string would have to appear in your table.
Yeah. Oh, okay. Yes. In that sense, yes. In that sense, I mean, it's a consistency about this guy and this guy.
I'll ask you.
Yeah. Anyways, so
independent dependency. That's it's a tuple generating dependency. That's what.
Yeah, I'm going to skip those because I don't have time. Nice, but I don't have. So using this framework. So this framework can be used as sort of a semantic structure now. And using this as a semantic structure, there's a powerful tools available to sort of detect or prove contextuality. So for instance, go back to this example and observe that those blue sections satisfy this equation, x plus y equals 0 mod 2, and those satisfy this equation, right? So going back to this example, this model can be perfectly described by those 4 sets of equations. Because those blue satisfy those blue, and this and this satisfy red equation. So yeah, so this model called PR box satisfies those 4 equations. Now, but those 4 equations must entail that if you sum up the left-hand side and the right-hand side, they must be the same. That's what is entailed by this set of equations. But they cannot be because, each variable occurs twice. So it cancels out. It's 0 to the left, but 1 to the right. So they are inconsistent with each other. So the upshot is that there is no global assignment consistent with all those 4 constraints. That is, there's no global section. There's no global section to this model. That is, so this the inconsistency of those equations are going to detect the strong contextuality of the model, or prove the strong contextuality of the model. Yeah. So and actually this method is going to subsume all the previously known examples of strong contextuality argument in quantum mechanics. So this is quite a powerful machinery. And also you can sort of relax the vocabulary, then you can cover many more examples, but that's not quite the point today. So this is the previous work. So today I'm going to, I have I don't know, 6 more minutes. I'm going to give you one small reflection about what is going on in this contextuality argument, because think of, okay, so this is the argument. Observe, note that this inconsistency, usually in logic, inconsistency means that there's no model, right? But it doesn't mean that here, because this inconsistency doesn't mean that there's no model satisfying those equations. Look, there was a PR box satisfying all those equations. Or if you put it in, say, entailment form, the entailment form doesn't mean that all the models satisfying the antecedents are going to satisfy the consequent. No, it's counterexample. So the point is that all those contextuality argument we saw is not sound. I mean, the logic of the contextuality argument is not sound with respect to contextual models. Well, that's the whole point of the argument, though. I mean, look, this is a classical logic, and the classical logic is violated by those models. Therefore, it is not a classical model. That's the whole point of the argument. But now, so that sort of that gives rise to the question that, okay, so what will be the logic of those contextual models? So on the one hand, we have this conventional global logic for global sections, but now we are in search of a sort of new logic for contextual models. Okay, so that's the question I'm going to review in the rest. Okay, so how to proceed? How to proceed? One observation to start with is that okay, this is globally sound, but not sound with respect to, I mean, contextually locally sound. Okay, I mean, there's a counterexample, but if you look at this set of equations, this pair of equations, then this is actually not just globally valid, but this is locally valid, contextually valid, because this is going to say that there's no section above this context. Right? This says that A0 and B0 are correlated and anti-correlated, so there can be no section above this context that satisfy both of them. Okay. So the point is that the sound logic of contextual models can be based on the fact that if those sentences are only talking about formulas that only talking about contexts rather than global set of all the variables, then you can still talk about them. I mean, valid logic of them. Okay, so this is the upshot, right? Inference within a context is about local sections, therefore they are valid, not just globally, but also locally, because they are valid about those sections. But also, this is another interesting point, that local inference can also go across different contexts in the following way. So compare this set of equations, or say this inference. This is valid. I mean, as we saw, this is invalidated by this contextual model. So this is only globally valid. But now, think of adding one more context here, so that those three, the combination of three is a context, and this is a context too. I mean, adding a Charlie, so that you can measure those three measurements at the same time. And replace, I mean, take this one, just replacing B1 with C. Then it turns out that this inference is valid with not just globally, but also locally for the following reason. So you can decompose this inference as this way. So starting from this part, those three formulas are about this context. So this is not just globally but locally valid. If you take this one, then this is not just about this context but also this context too. But now you see this, then you can combine this. I'm putting this under the rug, but now combine this one to this one, then those three equations are about this context again. Therefore, the point is that we just passed information locally from this context and then derived something about this context, which is also about this one, and then passed it on to this context, starting from the larger context and smaller context and the larger context again. So I call it, it's the same shape as this the locomotion of this worm, so I call it an inch-worm logic. But anyway, that's
A few minutes.
A
few minutes, yeah.
Okay, all right. Okay, so let's maybe I should start wrapping up. So this can be done. Actually, this logic can be done in a general setting using just regular language. But I'm going to, well, maybe I should say something about that. So the essence of this inch-worm logic is passing information from a smaller context to larger context, and larger context to smaller context. So there are two operations involved. One is starting from a smaller context and send a sentence to a larger context. But also, you should be able to come back, and that's exactly captured by existential statement, because that's a left adjoint, and this encapsulates all and only information that is given here about this one. And it should also, this has to be satisfied, because if some sentence is both about this one and this one, then going back here and coming back here shouldn't change the meaning of the sentence, and so on. And so everything can be done because this is regular logic, it can be modeled in a regular category, but the point is, well, okay, so it's a sort of a generality that is useful, but I will talk about sort of the rough idea of how the logic goes. So the point is, so the logic, we are going to define syntax, logic, and semantics of this inch-worm logic as kind of a parasitic to a global logic. So you start from a logic, and then you parameterize them into sort of a fragment, inch-worm fragment of them. So we start from the usual language, and then you are going to take each context or each valid, not valid context, but the legal context, and you're going to take all the formulas in one legal context or another, and then we call it contextual language. So you start from all the set of sentences, and then you're going to say, hey, this is a legal fragment of the language. Now, so for instance, this is legal, this is legal, because they are both about the valid, of the good context, or in the simplest is in the model. But this is not, because this cannot be in the context that is jointly measurable. Right? So this is good, this is not, and then you're going to take a inch-worm fragment of weaker logic as follows. So the first thing is that so you start from a global logic. You start from a conventional logic, and you take that when an inference can be done within a legal context, then that's a good inference. So for this is an example. But then you're going to be able to chain this good inference and this contextually good local inference in this way with with the condition, without, the witness, context witnessing this part and this part may be different. So that's how you can start from one context and move in inchworm wise, and then you can, this is also moving. So this is a chain of this inchworm movement, and then that gives you this inchworm logic. And then you can sort of define semantics in the obvious way as a fragment, and then you get a completeness theorem in a really parasitic way. So let me just wrap up with a statement. So suppose you start with a global logic for which you can just apply the usual categorical logic method to get a classifying or conservative or canonical model. Then in that canonical model, every completeness about the inchworm part is satisfied by that model. So you're going to get a family of completeness theorems in a way parasitic to the usual categorical completeness theorem. For instance, if you start from a regular logic, then the usual categorical logic gives you a classifying regular category for your theory. Then that theory, if you take a fragment, inchworm fragment of that, then it is already a classifying model for your inchworm logic. That's how the completeness goes. I will stop here, I think. Yeah, is that good? All right, thank you.
Questions, please, Ross.
So you might have said this and I just missed it. Does this inchworm logic, does it have cut elimination?
Good question. That defines, that depends on the formulation, but here, cut elimination in general is not, because you have to take care of the, do you think this is cut?
Yeah, okay.
Yeah. But you have to sort of, somewhere you have to take care of the fact that the every step is good within some context or another.
It's a lesser question, more a comment. It's just purely formally, the logic you're describing has has flavors similar to what you see in hyperdoctrinal treatments of constraint systems.
I see.
And anyway.
Yeah. That may. So this parasitic construction is sort of a indirect way of getting a sort of a hyperdoctrine issue structure for this logic, because you have a different space and algebras for different contexts. Then those are parametrically composed them together, sort of respecting no signaling. So yes, that sounds quite similar, even though you still have a you still have to distinguish between global validity and a local validity.
Can you go back to the tetrahedron thing that you had about information transfer?
Oh yeah, sure. Yes. Here, yeah.
Yeah, I was just trying to understand this bit. Can you explain the thing about passing on information from like that phase to that other phase?
Here to here?
Yeah.
Okay. Look at the set of variables occurring in here. That's all contained in this context, no?
Yes.
Yeah. Therefore, this is an inference about a section, local section sitting on top of this context. Yeah. So if this, this means that A0 and B0 must be correlated, and these must be correlated, therefore these must be correlated. So all the possible sections sitting on top of them must obey that inference. Now, once you get that, then this guy is about here, right? And moreover, that guy is also about here too, right? So you have to use a no signaling, but once you do that, then you have eliminated all the sections even above here, that violates them.
No, okay. By that you mean that you're assuming the same value.
Yeah.
It's constrained propagation.
Yes, constraint propagation.
One last question for here.
So, I'm trying to understand what this logic is trying to do. The first part you described about local consistency and global consistency, of course, is what people do in constraint satisfaction. And many of the algorithms for solving a constraint satisfaction problem involve constraint propagation.
Yeah.
Is this logic the proof theory of constraint propagation? Is that what's going on here?
That's what I'm trying to. Yeah. I mean, in a way, sensitive to in the inference that is sensitive to the propagation of constraints. Because you just write down all the constraints and ignore the topology of how the information is propagated, then you can, for instance, sometimes delete all the delete too much information. If you add, so the point is that in this model, you just write down all the constraints and just apply the logic without regard to the topology of the propagation. Then you're going to say, no, this constraint entails that there cannot be no model at all.
It's constrained propagation. It's constrained.
Yeah, that's right. Okay, that's a good way of putting it.
But you now also models which are globally consistent.
Yes.
Instead, it's not the case in classically constrained propagation.
Right, that's true.
It's true that you can have some rule for constrained propagation, and after applying the rules in not possible way in unbound number of times, you arrive to something which is stable, but not necessarily is the solution.
Global solution, that's right. So that's what
the global solution does not exist. You still.
Yeah. That's this characterization result about no signaling, because I can characterize no signaling as sort of a stability under a propagation. If there's no job for an intuum to do, then the system is already no signaling. So once you apply all the this intuum logic to everywhere, and if you get a stable solution, then that's going to give you a no signaling model, which may not be classical, but still it is good in some contexts like quantum or relational databases and so on. Yes. So this logic is how to did I answer your question or?
Let's
yeah. Sorry. Yeah. Thank you.
Thanks.
Yeah.